So I'll try to say something about the physics of the water, energy, land nexus, and whether it can be used as a basis for the analysis of land issues, and to what extent. So the first thing would be the definition. What is a nexus? I mean, many of you may know, but I just checked it in the dictionary, and I found that the nexus is a connection, or it's a connected group of elements within the context of a system, in this case, water, land, and energy. Now, certainly, they are really connected. All land-use systems have land, otherwise it's not a land-use system. It is connected to energy because the sun is there. If the sun is not there, then you can't grow any plants or anything, and it's not very interesting then as a land-use system. Water is there, rainfall is there. If there's no rain, there is no plants, there is no animals. So water and energy are definitely part of most of the land-use systems that you can think of. Energy and water are also closely linked, because if there is no energy, there is no evaporation, there is no formation of clouds, and that means there is no hydrological cycle, and there will be no rain. So it is very clear that they are closely linked, and also under threat. I mean, they are part of the environment, and they are under threat. So it is very good to try to use that as a basis for informed decision-making, or at least to be aware of the effects that your decisions may have on water, energy, and land, or our decisions. So first, something about water. When you look at the water cycle, then you talk about the hydrological cycle. That is an area of study in itself. What is probably important for the report is the land-water-atmosphere interactions, because they are a very important part of the climate change and of climate models, and one of the less understood parts. Water quality is important. Soil-water balance and water use efficiencies are important in land-use systems, especially agricultural systems. Soil and water conservation is very important in areas where there is not much water. And it is also in line with the sustainability of one of the objectives of the report. Water harvesting and small reservoirs is very important in West Africa, in areas where there is not enough water. Now, when you say water, you think of the oceans, and you say, okay, there is enough water, no problem. But we talk basically about sweet water that doesn't contain salt, that you can drink, and that's only 2.5% of the water on the globe. And then, unfortunately, or not unfortunately, but 70% of that is in the form of ice. So it's also not accessible. So of the total amount of water in the world, there is less than 1% is liquid water, such that you can drink it. And so it is, I'm not saying it's scarce, but it certainly is limited. And in some areas in the world, as you know, water is very scarce and is even more expensive than petrol or oil. Other parts have enough water. But often there is a distribution problem also, so the availability of water is more or less of a distribution problem, but the resource is limited and the quality is uneven. So the hydrological cycle, as you can picture it here on this picture, there is the sea here, there is the formation of clouds, and they go to the land, it rains, water comes into the vegetation, plants and animals can use it, comes stored temporarily in lakes or in the soil, and then it flows, whatever is extra or additional, flows from rivers to the sea. So this is the sort of cycle idea. And the sun is there because that's the source of energy that makes it all go around. The sun wouldn't be there, there would not be any movement of water. You talk about the land use system of a smaller size, say a farm or a small watershed. Let's say a watershed, then what is important there is the rainfall, that is the precipitation. Evaporation and transpiration. Transpiration is by crops, evaporation is from the soil. Is there that the formation of clouds? Evaporation is a function of temperature, so if the temperature is going up, you get a higher rate of evaporation, which means that even if the rainfall is constant and the temperature is increasing, that there is less plant available water. So even if the amount of water remains constant or the rainfall is constant, if the temperature increases, your losses due to evaporation are larger than they would be at lower temperatures. The vegetation is very important, and that also protects the soil against erosion. Then the water can be stored in the soil. It can go to the groundwater, shallow groundwater, deep groundwater. And there is runoff from the surface and subsurface to rivers and lakes. Energy. And that is a difficult one because I think many people talk about fossil energy only. But energy, the first source of energy is the sun, and that we all use, and that is very important in land use systems, of course. And that source of energy is generating plants and biomass and so on. And biomass is a source of energy that is for animals and humans. So, and also there is the whole report is written against the background of climate change. So I think it is good to start with the global energy balance. And then land use, land cover is very important in that balance, as I'll show in the next slide. And these greenhouse gases, of course, are seen as one of the main causes of the warming of the Earth. Aerosols, dust coming from bushfires and wind erosion. Evapotranspiration, as I just mentioned, formation of clouds, also linked to the energy balance. Then is the use of fossil and renewable energy in agriculture. Well, let's say in Europe, the use of fossil energy is quite large, through machinery, but also through fertilizers, like nitrogen fertilizers. But in Africa and West Africa, where they don't use fertilizers or hardly any fertilizers, and where there is no machinery, then the use of fossil energy is practically zero. It's only seed, the labor of the farmer, and the solar energy and the rain that make the system go. In addition, there is the issue of the production of sources of energy, like food and fuelwood, but also this biomass, these oil crops that you can use for this biofuel. Okay. Earth's energy budget. I won't say too much about it, but there is the incoming radiation of the sun, there is reflection, and there is absorption. And about 55% reaches the Earth, about 4% then is reflected, and then the rest is absorbed by the land, and it goes back as long-range radiation and as latent heat, mainly in water vapor. One thing that you should note is that if the surface of the Earth is white, then this one will be much bigger. So, and that we, as we will see in the next slide, I think, means that the Earth will be cooling. So that's a way of compensating for the heating of the Earth. The balance. Now, if the temperature on the Earth is not supposed to change, then the amount of incoming radiation should equal the amount of outgoing radiation in all forms. If the balance is positive, you have warming up. If it's negative, you have cooling. And when there is a difference between the two, the influx and the outflux, efflux, you talk about a forcing, a radiative forcing. Just to show you the order of magnitude, most of the warming up is caused by these gases, like CO2 and NOx and so on. This is the warming up, and that is mainly formed by these gases. But there is also cooling off of the Earth, and that's formed by these dust and aerosols and so on, and reflection of radiation. The net effect now is positive, so that's a warming in the radiative forcing. But we have to realize that there is also anthropogenic influence on the reflection and the absorption in other parts of the atmosphere. So what we know about climate change basically is the only thing we're really sure about is an increase in temperature. And in Africa, that's about 1 degree in close to 100 years. And it is also shown by models, but also in other ways by simple science, that it is both due to natural forcings and human forcings, anthropogenic forcings. So that's an increase in temperature, and it will continue to increase. I mean, there is no doubt about it for a long time. But the rainfall, which is basically, in a sense, certainly in the short run, the next 100 years, more important to agriculture and forestry and everything, land use, there is a lot of uncertainty. And you look into the future, so you have to work with models, and models, are not much better than their assumptions. So, but what the models would show for Africa, in this particular case, is that now my pointer is gone, but anyway, in Africa, in West Africa, it's white, which means that 2 2/3 of the models do not even agree on the sign of the change, whether it will be wetter or drier. If it is dots, then 90% of the models agree on the sign. So what you see here is in southern Africa, in our winter, which is their summer, they do agree on the sign, and it will be drier, which is not good news, although most of the rainfall is in the winter. But the rest of Africa is almost all of it is white, and which means that there is simply no basis yet in the models to say whether it will really be drier or wetter. West Africa in the summer, which is the rainy season, is also white, although there is a small spot that is green that looks like it is Ghana, which then they are lucky because then they get 10% more rainfall. But this, of course, is very high a degree of insecurity. But the striking point here is the white surfaces in Africa. The climate models and the global circulation models do not even agree on the sign of the change in rainfall in 2/3 of the cases, or more than 2/3 of the cases. So a lot more work has to be done there, and we should be a little bit careful when we talk about drier and the consequences for the agriculture and so on. However, having said that, almost all the models agree that south of the Sahara, in the Sahelian zone, it is likely to be drier. So to interactions and links, so the land and water play a role in the energy balance. I think I've shown that, and that's very important. And also contribute to the elements of climate change. So through your interventions in land use systems, you can also have an effect or influence the climate change in a positive and negative sense. Interventions or work you do on the surface of the earth and on the land may use energy, fossil energy, in transport machinery, in fertilizers, nitrogen fertilizers, if they are used. But most of it is the sun, solar energy. So that is fairly environmentally friendly. And you use it for photosynthesis, which then generates energy in chemical form that you can use for feed and food. Interventions at the surface of the earth may also generate source of renewable energy. I just said food and feed, fuelwood, organic waste, and oil crops for these biofuels. Land, that is the heart of the systems we talk about, land use systems or ecosystems, and the focus of this chapter. So land, what is very important is the productivity of the land and the degradation of the resource. That's an area of great concern. Forms of degradation are the loss of the vegetation, erosion, the loss of surface soil through water or wind, deterioration of the physical, chemical, and biological properties of the soil. I'll not go in detail, but those are also very serious because they affect the productivity of the soil. Soil and water conservation is an issue separate. That is, you would recommend that in areas with low water availability. And the carbon and nitrogen cycles are very important because they affect the heat balance and therefore the issue of climate change. Well, you know, the carbon balance is CO2 and the nitrogen balance is N2 or NOx. Degradation of the soil. This map was originally developed by ISRIC, I think, Wim Sombroek and his team of experts. It's an expert analysis, and it wasn't really based on measurements in the field. And when it says whether it is red, which is the most serious class of degraded soils, it can be different things. It can be chemical degradation, can be physical degradation, it can be loss of vegetation or whatever. So red in Europe doesn't necessarily mean the same as red in Africa. But what the picture shows is that soil degradation is a global phenomenon. It occurs almost everywhere except in Siberia and in Canada and Alaska. And it is a very serious matter that affects the functioning of the ecosystems to all sort of degrees. Now, it's especially serious in the semi-arid area, in the Sahelian zone, and south of that in sub-Saharan Africa, Chile. It's serious in areas with high population pressure, often like in China, Mexico, India, and deforestation where that occurs, which is a form of land degradation. And the data go back to the Glassot study in 1997. Deforestation, just one example. This is in Ivory Coast, Côte d'Ivoire. And in 1955, the forest, that is the natural forest, was still covering most of the area in the south of the country. And in 88, it was 33 years later, it was only these remnants in the west of the country where there is some closed forest, but the rest is almost gone. And in the meantime, we are at 23 years after this, so you can imagine that not much is left of the original forest in Côte d'Ivoire. So we also don't have to worry about its conservation anymore. There is the carbon cycle, a very important one, emission of CO2 and CH4, and methane from inundated soils like rice soils, mineralization, immobilization, or sequestration it's sometimes called, but in soil science it used to be called immobilization. That's the incorporation of carbon in organic matter or in plant tissue. That is, these organic compounds are a source of energy for all the living organisms in the soil, so very important there. Organic matter is important for the quality of the soil, the physical properties, the chemical properties, and for the availability of trace elements to plants, because they form sort of complexes that are soluble in the soil solution and can be used by the plant. Otherwise, the plant wouldn't be able to take up any of those elements. So it's very important. It's very difficult to overstate the importance of organic carbon in soil and land systems. This is one picture of the CO2 cycle. You see the photosynthesis, sunlight by trees and plants. Then it enters into the soil as dead matter, decay. Then respiration, which is the reverse process of photosynthesis, almost, so to speak. It will generate CO2 and H2O. So the CO2 goes back to the atmosphere, and then you are round. Or that's also sort of a cycle. Now, an interesting thing here is that to note that the total amounts, it's not just the flows, but it's also the sinks or the amounts that are stored are not so much in the atmosphere. It's less than 800 GT, gigaton. And what is stored in vegetation and in soil is about 1600 GT, so that is more than twice as much as in the atmosphere. But in the ocean, it is 38,000 tons. So what is in the atmosphere is 1% or 2% of the total amount of sea. But the exchange with the CO2 in the deeper layers of the ocean is very slow. So it will buffer. If you lower it in the atmosphere, ultimately it will buffer. It will all come back. But it takes a long time. And to immobilize it in vegetation, in trees, that's a matter of a few years, and you have sequestered or whatever, sequestrated or immobilized then the CO2 or the carbon in organic matter. But it's good to realize that the largest amount, by far the largest amount, is in the oceans, and next one is indeed the vegetation and the soil. The nitrogen cycle, and you can write books about it. In fact, different books have been written about this. For us, the interesting part is the NO2 here, yeah, that is to the right, on my right, yeah, you're right. N2, N2O, that is the denitrification of nitrate, and the immobilization in the organic matter. The two main forms of mineral nitrogen in soil is nitrate, and it is ammonium, and ammonium can volatilize as a gas, NH3. If that comes back to the soil, you get acidification of the soil, but that is being under control somewhat these days. It can be fixed by clay minerals and can be incorporated in the soil. It can nitrify and can be taken up by the plant. And nitrate can be taken up by the plant, can be immobilized in the organic matrix. It can leach because it's an anion, so it is very mobile in the soil. And it can denitrify and then give NOx, and that is a greenhouse gas. This is a picture again. Yeah, I don't have oh yeah, there it is. It's funny. So this is the fixation by rhizobia, bacteria in the soil. That they fix nitrogen. Lightning will give ammonia or so in the soil. So what is called soil nitrate here is basically all mineral and nitrogen in the soil. This is the sort of circle. It's taken up and then in decay it comes back. Here, denitrification in swampy areas or in rice soils or in any sort of inundated situation with low redox potential will give you NOx, and that gives atmospheric nitrogen again, or it can come back. Now, you don't look at land, water, and energy in isolation. You look at it in a systems context. And one example of land use systems is the work done by FAO in the LADA project, and that's funded by GF, UNEP, and FAO. This is land use systems in the whole world, about 40, 50 systems. This is the picture for Africa, and the green colors is largely the humid tropics and mixtures of forest and agriculture. Only these dark green spots are the remnants of the forest in Africa, so you can imagine what has been, what is all lost, the whole green area, the Congo Basin, and the West African forest. The yellow color is savanna, and brown is bush savanna, and the pinkish colors are agricultural systems with very little trees in it. So this is the legend. It can be downloaded from the web, as I've done it. It's about 40 systems distinguished here. Another example of land use systems or of classification is also by FAO, and this is following the agroecological zones in West Africa that all are parallel to the Sahara, and the rainfall will increase from the yellow and brownish colors to the coast. This is an increase in rainfall. So it's important to, if you look at well nexus, to define a system. So you define the system, and if you define a system, you have to define the boundaries, and you have what is not system is then the environment. A system, by definition, is a part of the reality of nature. So a useful tool to analyze systems, and in our case in particular, the sustainability, is to look at the principle of the conservation of mass, which basically tells you that the amount of matter that enters the system and that leaves the system, influx minus efflux, is equal to the accumulation of that component in that element of volume or depletion, depending on what happens. Now, if your source sink term is 0, which is often the case, unless you talk about radioactive compounds or so, then you can say that this is the equation. Influx minus efflux is what is the change in the content of that compound or that element in the system. If efflux is influx, if that is equal, then this is 0, and then there would be no accumulation or depletion, and this is basically a sustainable system. But influx, it is also possible that if there is accumulation, that it doesn't harm the system, say on a time scale of 100 years, and that in that case it can also be sustainable if you define that as no major changes within a century. Now, two examples of systems. One is just a natural forest. There is solar energy, no limitation. There is rainwater. There is water through respiration and evapotranspiration, I should say. CO2 is being used in photosynthesis, but also through respiration it enters into the atmosphere. No problem. Oxygen, which is very nice. Leaching is limited, some water maybe, but the nutrients, most of the nutrients are really caught by the roots of the trees. The trees are deep rooting, so they catch most of the nutrients. So this is a sustainable system. If it is a field crop, you have the same situation, but then you add fertilizer, generally mineral fertilizer, and you export part of the biomass, and that means you export carbon and other elements, NSP, and calcium, magnesium, sodium, potassium, and microelements. So in this case, it's only sustainable if this equals this. I mean, if the amount of minerals that you bring into the system equals the amount of minerals that leave the system. Now that is, and if that's equal, that's sustainable. However, if you expand your system and you include something like the phosphate deposits in your system, then you're depleting your phosphate deposits to generate this. So unless the phosphate in your biomass is returned to the soil or to the system, that situation is not sustainable because you're exhausting your phosphate deposits. But if you look at a farm, as long as there is fertilizer on the market, this is sustainable. I mean, if you assume that will be for 100 years or so. So general systems you have, you look at energy, land, and water in the system, you look at inputs and outputs. That can be anything, not only mass and energy, but also agricultural outputs, inputs, labor, machinery, credit, knowledge, livestock, pests and diseases, all can enter and leave the system. And what's worse, the environment can also change, as we know, that is the climate change. So this is a prediction of the decrease in productivity in over, I think, 100 years. I can't read it well, but the brown area, which is bordering the Sahara, which is the Sahelian zone, and it goes around in Africa, as you know, that is the area where they expect a significant decrease in the productivity of agriculture, mainly because of the drier conditions. This picture by Phil Thornton of ILRI is even more gloomy, so to speak. The whole brown area is a decrease of 1 to 20%. It is basically all of this area. Only in the humid area there is a small increase. But here there is a 100-day decrease in the growing length of the growing season, which is very, very serious. So, but this is rather speculative, but it should not be ignored. And already agriculture in the Sahelian zone is not very, very good business. So if it becomes drier, it will be very difficult for these poor people. You have to look at scales in space and time. I just mentioned this one system. A small system can be sustainable. A bigger one cannot be, or it might not be at the same time. All the processes that occur in these systems are defined with regard to space and time. And if you want to move from one level to the other in terms of scale, you talk about upscaling and downscaling. And it's important to know that when your level of focus, your level of focus is at the higher end. It is at the larger scale is basically controlling what is happening at one level below that you look at, and a level at the lower level. It explains what happens at this level of focus. So systems always have this scale issue. Spatial scales for us, or this was basically developed for a presentation on climate, but so we also have less than 1 kilometer. It's a plot scale, but these are scales, spatial scales. If you look at these global circulation models, they're at the higher end, and below is on the bottom is the small watersheds. Upscaling, downscaling is the issue here, and that is a very, very difficult issue because the physical processes are not really continuous, so you have to develop mathematical formalisms to do that. Timescale, this is a 1-year timescale for the rainfall in Tamale in the middle of Ghana. You see a tremendous difference here, about 1,600 millimeters in 1 year, and the next year you got 700. So in one case you have floods and inundation, and in the other case you have a crop failure and famine. If you put the time scale 5 years instead of 1 year, your whole thing is gone, or almost. You make it 10 years, you would say, well, beautiful, but then you can't explain why you have a crop failure in 1 year and floods in the other year. So the time scale just is also very important, and depending on the objective that you use it for, you do that. Now the criteria that you can derive, I used keywords: integrated NRM, sustainable development rather than growth, increase in scarcity and climate change, and then just by common sense you can derive things like that. You have to decrease the emission of greenhouse gases to the extent possible, and so on. I mean, all of you can think of this, but you need something like criteria for the decision making. But they follow directly from these considerations. Now, once you've done that, you have defined your systems, you understand your water, energy, land nexus, and you have looked at the criteria, you know what to do in what cases. Then you optimize the functioning of your systems in terms of water, energy, and land, and you derive management strategies from that. I would like to end with one social science type approach, which we also do. I mean, I'm aware of the importance of social science in agriculture and in land management. Just one, this is about low external input sustainable agriculture, LISA, or whatever you pronounce it. Fertilizer use in 2005 to 7 in the Netherlands was 892.4 kilograms per hectare. Hold that. Niger was 0.4 kilograms, and in Mali it was 0 or 0.0 kilograms per hectare. That's what you have to keep in mind in the whole discussion here, incidentally, and so on. And of course, you all know it, but it's good to every now and then put those pictures again or those numbers up. So basically, all of the agriculture in Africa, other than in the Republic of South Africa, is LESA. It's low external input, or it's almost zero input in many cases. So I would like to emphasize that low input agriculture in Africa does not mean zero input, but it means that you may have to increase your inputs, even though you talk about low external input agriculture. But in many cases, you also introduce other technologies, like using more organic residues, introduce lower zero tillage, and mulching, for example, for moisture conservation, alongside the use of small quantities of mineral fertilizers and the use of improved maize varieties. That was the program that I had the pleasure to evaluate half a year ago, the Sub-Saharan African Challenge program, which is a program in 8 countries, and it was for 10 years or so. Now, I would like to say this, that I've worked for most of my life in international agriculture, and we always were faced with the linear approach to technology transfer. International institutes talk to national programs, the National Agricultural Research Institute. They talk to the Extension Service, they talk to the farmer. If these people don't talk to these people, then it stops. There is no technology transfer, at least not from the international science. If they don't talk to the Extension Service, then there is no input of technology there, new technology, so they have nothing to say. If they don't go to the farmer, or they don't have money to put petrol in their car, which is very often the case, or if they have the money to put the petrol in the car, they take their girlfriends out for lunch, then the farmer doesn't see any extension agents. And this system has not been very successful. And one of the reasons is that this doesn't work, or often doesn't work optimally, but also that the farmer, to introduce changes, needs access to rural credit, input markets, the policies, subsidy policies, output markets. So it simply didn't work. And in this project that we did evaluate, and that was funded largely by the European Union, what I did was this innovation platform approach, to some extent developed by the Royal Tropical Institute, it's gone, but, it's simply putting everybody around the table. Let them talk together. And that also means that the extension agents, who usually say, you know, this is our responsibility, nobody touches what we do, they have to work as facilitators. And it was really fantastic to see that happen. I mean, I've seen it in Malawi, in Mozambique, Nigeria, Niger, Zimbabwe. So everybody around the table, and then you find solutions. And there is a lot of literature on this now in the meantime, and we also have our report finished. But I was very happy to see that it worked in many cases. And this was the first time for me, at least in Sub-Saharan Africa, that I saw a simple technique work in terms of transferring technologies to farmers, involving the private sector. And also it looked sustainable because it was the farmers themselves that organized themselves and did it. It was not other people that did it for them or that gave them money to do it. So, probably you can find it on the web under Sub-Saharan Africa Challenge Program. So this is where I would like to end. The last observation is that the well nexus can provide a framework for the analysis of land issues based on an understanding of the roles of water, energy, and land, and on their links and interactions in well-defined land use systems, clearly related to spatial and temporal scales. Criteria for analysis and development of governance and management strategies would not be very different probably from those derived earlier from the Millennium Ecosystem Assessment. I'm just saying that because that provides a systems environment. You can still focus on the WEL nexus, but the Millennium Ecosystem Assessment did analyze systems in terms of products and services, and that provides you with a handle to say, okay, this is how we want to manage the system. We want to optimize water quality or the production or whatever. So, and I think poor countries in Sub-Saharan Africa would still need some assistance from Europe to implement sustainable development policies and management strategies. Thank you very much for your attention.